So, welcome to this next lecture on power attacks. So, we shall be continuing our discussions on power attacks on the elliptic curve hardware. So, in the last class we were discussing about power attacks or simple power attacks on elliptic curves. In today's class we shall be discussing that those designs are still vulnerable against DPA, and therefore, we shall try to see how we can protect them, and we shall be considering some more improvements in the attack. So, to start with, right, I mean essentially today we shall be covering these concepts. So, we shall be looking into DP on ECC, we shall be talking about a specific way to implement the elliptic curve hardware, which is called as Montgomery's ladder, and we shall be trying to look at it in the context of power attacks. We shall be trying to look at an interesting technique of protecting against DPA, which is called as Coron's blinding technique, and we shall be also reflecting on an attack which is called as doubling attacks, which is relevant on the Montgomery ladder, okay, and also maybe relevant on the Coron's blinding technique. So, let us see, this is essentially this what is called as a Montgomery ladder. So, in Montgomery's ladder, the idea is that you again this is a type of algorithm where you do both doubling and addition, okay. And the interesting thing is that I mean there are essentially, right, you can as we you can actually implement it in a very efficient manner, okay. You can essentially, like if you are using projective coordinates for elliptic hardware, then you can as well do this without the y coordinates, okay. Therefore, you can actually remove one of the coordinates and you can still do it, you can still implement it, okay. But today we shall be discussing this more from the context of power attacks, but first let us have a quick look to understand that we really understand how the algorithm works, okay. So, therefore, this is your scalar, that is d is your scalar, which is d is equal to, this is a binary so as we have done, right, we have basically taken d and we have written it in the binary format. So, therefore, suppose dk minus 1, dk minus 2, so on till d0 is your scalar that you have, and dk minus 1 is 1. So, therefore, we are assuming that dk minus 1 is 1. So, we will be starting the processing from k minus 2, okay. So, what we do is we basically initialize Q1. So, now we have got two registers Q1 and Q2. We initialize Q1 to P and Q2 to 2P, okay. And the idea is that if di is equal to 1, then we are basically adding in Q1 and we are doing doubling in Q2, whereas if you are doing, if like your di is 0, then you are basically adding in Q2 and you are doubling in Q1, okay. So, this form of representation is very efficient, because like you can actually implement this loop also in a slightly different way, where you can remove this if statement, okay. You can actually write this in a way such that the suffix of the registers Q1 and Q2, you can use it as the key bit, okay. So, that means like you can write something like QB, where B stands for the secret key bit, okay. So, this I am not elaborating at this point, and I kind of leave it as an exercise to think how you can write this Montgomery's ladder without the if statement, okay. So, but rather what we will be looking at in today's class is that if you observe that the reason why the SPA was originally working is because there was a conditional statement where you are doing an conditional whether you are doing the addition depends upon the secret bit, okay. But here you can observe that irrespective of whether the key bit is 1 or whether the key bit is 0, you are always doing an addition operation, okay. But in one case you are doing addition in Q1, in the other case you are doing addition in Q2, but you are always doing an addition operation, and therefore, you do not get that clear power signature to distinguish between and understand what is the secret key bit, okay. It works correctly. So, let us take an example. Suppose your key is 91001. So, that means we will start processing from this 0, okay. So, our initialization is Q1 is equal to P and Q2 is equal to 2P, okay. And then since K2 is equal to 0, that means this is a 0, the secret scalar bit is 0, then what I do is I basically, if you see this branch, this is 1, so therefore, I come to this branch and therefore, I add in Q2, okay. So, I add in Q2 means that Q2 becomes P plus 2P, that is 3P, okay, and Q1 becomes the double of Q1, so Q1 becomes 2P. Then I get again 0, the next scalar is 0. So, therefore, I do essentially the same operation, that means I essentially add in Q2. So, Q2 becomes 5P and Q1 becomes 4P. Then I get a 1. So, now what I will do is I will add in Q1. So, therefore, Q1 becomes 5P plus 4P, which is 9P, and Q2 is 8p, but this we can use for if the scalar was longer, but then the result that we return is essentially Q1, because Q1 is 9p that we want to compute. So therefore, functionality wise this is correct, okay, and also it gives us an enhanced protection against simple power attacks, because there is no conditional statement, and therefore this seems to be more secure, okay. So now let us see, so basically now let us look at it with the context of DPA. Okay, so now again let's recapitulate DPA a little bit. So as we have already discussed, that DPA is essentially a more fundamental form of attack, because here we try to kind of exploit the fact that the power consumed is actually dependent upon data. So what we did, right, essentially is kind of shown here kind of informally as a procedure. So we basically gathered many power consumption curves as opposed to simple power attacks where we do on few power observations. We assume a secret, okay, so the secret could be in the case of block ciphers an n bit value, or in the case of a stream cipher could be a single bit. In the case of DPA also we will do something like what we were doing for stream ciphers, okay. That means we will do the attack in an iterative fashion. So we will assume that we know the till I bits, and then we will be trying to guess the I plus 1th bit. So therefore the guess is either 0 or 1, and we will basically trying to use this DPA or distinguisher to understand whether my guess is correct or not. So basically what I do is I guess this 0 and guess this, the key bit to be either 0 or 1, and then we basically have a target register or target computation. So now the thing is that if my guess was correct, then my target is correctly computed, and therefore, right, I will if I correlate it, if I extract out a hypothetical power from that target register and I correlate with my real power trace, then I should get a maximal correlation. On the other hand, if my guess was wrong, then that correlation will be much lesser, and therefore I can distinguish and understand whether my key guess was correct or whether my key guess was wrong, okay. So what I mean is essentially if I just take the simple scalar multiply algorithm, or the double and add algorithm. So what we are doing in the normal double and add algorithm is that you essentially are doing a double operation. So therefore if you have got a point P, you are doing a 2p operation always, okay. If your scalar is 1, that means if your di is equal to 1, then you are basically adding, right. So basically you are doing so this suppose I am like having a register and I am writing r equal to 2r. If this key bit is 1, then I am writing r equal to r plus p, okay. So basically I am trying to calculate lambda p or maybe dp in this way, right. I am trying to calculate dp in this fashion, okay. So therefore, right, it means that I have got the scalar d and I want to kind of add p d times, okay. So therefore, right here what I will do is that I will now guess this di, okay, and I will target this register r. This register r is constantly being updated. If my key bit was in the ith step was 0, then I would have got 2r, but now instead of that I am getting r plus p. That means this 2r is happening and then I am adding p to it, okay. So the idea is that if my guess is 0, then I will be basically like trying to kind of estimate what would be the value of r, and from there, so therefore my target register is, my target in this case is the register r, and from there I will be trying to predict what is my hypothetical power value, okay. So in case of CPI, you basically find out the hypothetical power value. In case of DOM, you probably target one of the LSBs of this R, okay. Suppose this LSB is 0 or whether the LSB is 1, you take all the power traces, you basically make a 0 bin, you make a 1 bin, and then you basically like kind of take the traces and put them into the 0 bins and the 1 bins, you take the average, take the difference of means. The idea is that if your guess was correct, then difference of mean is quite high. That means there is a high correlation. In case of CPA, you basically take the entire value of R, we predict the hypothetical power value by some kind of power model, and then you try to correlate that power value with your real power trace. And the idea is that you probably calculate a Pearson's correlation and you find out that the Pearson's correlation should be maximized at some time instance, which is your point of interest, okay. So this is how you can adapt DPA to even elliptic curves, okay, and essentially the attack should fundamentally work, okay. So let us see how it will work. So what we do is that if I want to do a DP on the Montgomery ladder, for example, then essentially I again look back at the Montgomery structure and I try to kind of find out how the like the Montgomery evolves, the Montgomery ladder evolves depending upon my key bits, okay. So basically I start with my key dk minus 2 because that is the first key that I need to find out. So this key bit can be either 0, can be either 1. If I am not given any side channel trace, then I have got no clue to understand whether it is a 0 or whether it is a 1, okay, because because the algorithm is nicely shielding this this fact, okay, in a mathematical fashion. But then what I observe is that if dk minus 2 is equal to 0, then there are two registers like Q2 and Q1. Q1, for example, you can see is equal to 2p. Okay. On the other hand, if this bit is 1, then Q2 is, then you can see that this 2p, right, never occurs. Like you will see that if this is 1, then Q2 is 4p and Q1 is 3p. Okay. So therefore, right, if you observe, then rather than targeting or correlating with the value of 3p, it would be an intelligent, right, or it should be more sane to basically correlate it with the value of 2p. Okay, because if the key bit is 0, then 2p occurs in one case, whereas 2p does not occur if the key bit is 1. Okay, you can see 3p occurs in both cases. This is 3p and this is a 3p. Okay. So what I will try to do therefore is that I will be trying to kind of correlate it with 2p. If it correlates with 2p, then the idea would be that probably the guess is 0. Okay, I will return 0 as my guess. If it correlates with 4p, then I will return 1 as my guess. Okay, so I can also confirm whether my guess is correct in this way. Both of them, should confirm ideally. Okay, so this is a simple strategy that you can take, and you can try to kind of adapt your differential power attacks for elliptic curves, even if there is a Montgomery ladder implementation underlying. So therefore, right, I mean, with this, let us try to see again the setup. So in this case, again, we try to do a DPA with the real power traces. So in order to mount the DPA attack, we implement the Montgomery ladder on an FPGA platform, which is specifically designed for power analysis attacks, just like the one that we saw in some of the previous classes. So the board basically provides a 1 ohm resistor between the power supply and the VCC, okay, and pin of the FPGA. So we measure the current which is drawn through that resistor during the elliptic curve scalar multiplication operation by a current probe. So we use, as we discussed, current probes of proper specifications, so that there is a high SNR of your power traces. Okay, so we know what is an SNR, so that we would like that the power trace has high signal to noise ratio. And then, right, we basically try to measure the power in a Tektronix oscilloscope, or for that matter any oscilloscope which has got high bandwidth. So this is the oscilloscope that we use in our setup, and then we develop software tools to automate the whole process for varying inputs. Okay, now the power consumption is proportional to the voltage drop across the resistor and is measured in terms of millivolts, which is varied around 10 millivolts, and the power signal is also sampled at a high sampling rate of something like 12.5 megasamples per second. Okay, in our current setup, we essentially sample it at even a higher sampling rate. Okay, so therefore, right, once we have that, then we apply our DPA principle. So DPA principle is, as we have discussed, that with the same exponent d, you perform repeated operations with different p values. Okay, because the scalar is which you want to basically obtain is kept constant, and you are basically giving different p values, and you are computing different times you are computing dp, basically like multiplying p with d. So the attack first targets the secret bit dk minus 2, which is processed at first iteration. Okay, and thus we store the power consumptions during the first iteration of dp computations. Okay, now the power consumptions are then divided into two sets based on the specific bit, or LSB in our case, of 2p, because we are trying to correlate with the value 2p. Okay, we calculate the mean power consumption of each of the sets, and then the absolute value of the difference of mean power consumption is calculated as the difference of mean. Okay, and a similar processing also is done for 4p. Okay, so here we observe an result. So we basically show the differential plot when you are trying to correlate with both 2p as 4p. So you can see that we obtain a correlation with 2p. So 2p is the color which is shown in blue, and you get a high correlation. That implies that we will be returning 0, and that turns out to be the correct key. So therefore, on the other hand, right, there is no correlation with 4p, which means like that the key bit is not 1. Okay, so basically you can do both the tests and can confirm your guess. You can confirm your estimation. Okay, so So therefore, right, I mean, we understand that the Montgomery's ladder is vulnerable against differential power attacks, okay, although it is resistant against simple power attacks. But there is a simple technique, or there is a very nice technique which you can apply, which is called as Coron's point blinding method. Okay. So here what you do is you choose a random secret value R and compute S equal to dr. Okay. So note that what I just do is I basically choose a secret value which is R. So the design internally does that. Every time you are doing an encryption, ideally you should use a different R. Okay. And then you basically calculate S equal to dr. Okay. And then what you do is basically you blind the point P by computing P plus R, because P plus R essentially makes it kind of independent of P, because you are basically choosing a random point and you are blinding that point. And then you multiply D into P plus R, that is you calculate D into P plus R and you subtract out S. Okay. So you can easily see that this is nothing but equal to dP, because D into R minus S because of this equation gets cancelled out, and therefore you basically are calculating dP. Okay. But at every step you are basically doing this computation or you are doing this computation, both of them are essentially, right, ensuring that you have a random component which is coming into play. Okay. And the idea is that you basically would like to ensure that, as I said, that every time you are doing repetition of this, you should have a fresh random values. Okay. So therefore one trick that essentially you can do is you can use this equation to update your blinders or masks. Okay. So what I do is basically I take a coin like a bee, right, essentially is basically randomly sampled from 0 or 1, and then I basically do this operation, that is minus 1 to the power of b into 2r, and s dash is minus 1 to the power of b into 2s. So you can note that even with r dash s dash, this relationship, that is s dash is equal to d of r dash, is maintained, right. And therefore, right, you can use these two blinders also in the next step, where you basically calculate maybe d into p1, where you are like trying to calculate dp1. So dp1 you can calculate as d into p1 plus r dash and subtract out s dash from this, right. So therefore, right, the idea is that every time if you do this operation, then this would be naturally resistant against a differential power attack, because every time, because of this randomization, you are ensuring that the attacker cannot pick up these correlations. Okay. So therefore, right, I mean this is quite nice, and we basically, right, can probably expect that this will be more resistant against power attack. So you can see, for example, that in the same case when you adopt the Coron's technique, then there is like this, the correlations that we were getting to distinguish between the key bit being 1 or the key bit being 0 are now gone. Okay. With even quite large number of traces like around 20,000, there is no correlation with 2p or 4p, and therefore Coron's blinding technique works quite nicely. Okay. So there is another class of attack which I would like to consider here, and essentially is what is called as doubling attacks. Okay. So we will try to see how doubling works or how doubling attack works. So just remember that in the Montgomery's ladder, like when you essentially have the original Montgomery's ladder, so and this is more like useful for Montgomery's ladder, is that if your key bit is 1, you basically add in q1. So q1 is equal to q1 plus q2, and you double in q2. So you do q2 equal to 2 into q2. If the key bit is 0, then you add in q2. So q2 is equal to q1 plus q2, and you double in q1. Okay. So now let us try to see and see how the evolution works when there are two inputs specifically which are processing in the Montgomery's ladder. Okay. So in one case I am processing m, that is p equal to m. In the other case I am processing p equal to 2m. Okay. And the scalar that I considered is 1 1. Okay. So 1 1 followed by 0 0 1 0 1 and 1. So suppose this is my corresponding scalar which I process. Okay. So in the first case I said that this is 1, so I will leave this, I will start from this one. Okay. So because this is my leading one, so I can just leave it right at this point. So therefore q1 here is equal to m plus 2m, okay, and q2 is equal to 2 into 2m. Okay. Likewise, right, in the next case I get a 0 here. So if it is if it is a 0, then I will be adding in q2. So you can see that I add in q2. So q2 is equal to So in this case you have got 3m and you have got 4m. So I just get 3m plus 4m, and Q1 is equal to the double of 3m, because this gets double. So I get 2 into 3m. Okay. And then I have got 0. So again I have got 0, which means I will again be adding in Q2. So this turns out to be 13m, and Q1 is equal to 12m, because I am again doing double of 2 into 3, which is 6m. Okay. Now if this is 1, the next bit is 1. So I get Q1 as 12m plus 13m. So I am adding in Q1 and I am doing double in Q2. So this becomes 2 into 13m. Again I get 0. So therefore I add in Q2. So Q2 becomes 25m plus 26m, and Q1 is equal to 2 into 25m, right. Then you have got 1. So you have got Q1, which is equal to 50m plus 51m, and Q2 is equal to 2 into 51m. Okay. And next again you get a 1. So basically you do Q1 equal to 101m plus 102m, and Q2 is equal to 2 into 102m. Okay. So therefore you can verify that Q1 is equal to 203m, which is what we want to calculate. So this scalar should stand for that corresponding result. Okay. Now the interesting thing is that let us see the evolution. What happens is when you are processing 2m basically. Okay. So again we will do a similar thing. So we will start here with Q1. So Q1 is 2m plus 4m, and Q2 is equal to 2 into 4m. Okay. So that is my first computation which is being done. In the second case I get a 0 here. So therefore I do Q2, which is equal to 6m plus 8m, right. 6m plus 8m, 4m is 2m plus 4m is 6m, and then this 8m. So I add in Q2 because it is 0, and Q1 is equal to the double of 2 into 6m, which is 12m. Okay. So that ends my this processing. Then I get again a 0. So therefore I again add in Q2. So Q2 equal to 12m plus 14m, and Q1 is equal to 2 into 12m, right. So that ends my computation for this stage. Then I get again a 1. So because of this 1 I will add in Q1. So Q1 becomes equal to 24m plus 26m, okay, and Q2 is equal to 2 into 26m. Q2 gets doubled here, okay, and that is my ends this evolution. So then I get a 0. So Q2 is equal to now 50m plus 52m, and Q1 is equal to 2 into 50m. Okay. So that ends this evolution. Okay. And then you have got 1. So because of this 1 you will have Q1, which is equal to 100m plus 102m, and Q2 is equal to 2 into 102m, and that is obtained at this point. And then finally, right, because of this 1 you have got Q1, which is equal to 202m plus 204m, and Q2 is equal to 2 into 204m, and that essentially means this is your result. Okay, and that essentially is nothing but the result that you want, okay, which is the double of 203m. Okay. Now interestingly you observe that if the two successive key bits are 0, okay, and if you target the register Q1, you will see that both of them compute the same value. Okay. Like in this case it is 12m, this is also 12m. Okay. Here also if these are these two are ones, and if you target this Q2, that means whenever there is a doubling operation, you will see that the doubling, right, essentially has got the same result. Okay. So that means, right, we can write from here is this fact that if di minus 1 is equal to di, then same doubling operations, is executed, okay, is executed in the I minus 1th iteration of d into 2m, okay, and the ith operation of d into m. Okay. So, this is an attack which you can still try on the Montgomery's ladder. Now, interestingly observe that the way we were updating the mask in when we are using Coron's technique is that we had this r plus p. So, this we were modifying to r dash plus 2p. So, imagine that if you have got, I do a run with p and then I do a run with 2p, then this is what will happen, right. I will add r plus p and here I will add some r dash plus 2p, but the relation between r dash and r is given by this relation minus 1 to the power of b into 2r. Okay. So, with a probability of 0.5, we will still have that r dash is equal to 2r, okay, and that means you are basically processing 2 into r plus 2 into p, which is 2 into r plus p. So, here you are processing with r plus p, with a probability of 0.5 you are processing 2 into r plus p. Okay. So, therefore, right, you can still try to fancy an attack even when you have Coron's blinding protection, okay, and therefore, you probably need to do something better to update your blinding techniques. Okay. So, we will basically stop here and we basically we will just conclude what we discussed, and so basically what we discussed is that the naive ECC design is vulnerable to SPA. The Montgomery's ladder is a safer design strategy with respect to power attacks because it prevents against simple power attacks. Coron's blinding technique is an interesting way to protect Montgomery's ladder against DPA, and doubling attacks are more powerful DPA which are possible on Montgomery's ladder, and even right we still can fancy our chances on even if there is a Coron's blinding protection which is updated in the fashion that we described. So, the two references for this discussion are like the MS thesis of my former MS student. So, you can see this is the URL for that, and the PhD thesis for one of my former PhD students. Okay. So, you can go and see these references for more elaborations on these topics. Okay. So, thank you for your attention.